All right. Are there any questions? Okay. So last time I talked about, the Bayes classifier, right? And the error of the Bayes classifier is the minimum error that you can get, right, while doing classification. And here I'm going to give you some examples of, some classifiers that have structure in them, right? Because remember, we said that because of the small sample size, you cannot look for the best classifier, okay, because it's going to be too complicated to design, right? So you're going to look at classifiers that have certain structure, right? And one of those is what is called the QDA, or the quadratic discriminant analysis, right? Yeah, the gas leak is over there, so we don't need to do anything here, right? I mean, we're fine. So a classic example is the QDA, quadratic discriminant analysis, right? So to discuss or to introduce QDA, let R sub k. See, if you need to talk, just step outside, finish your discussion, then come back. So to discuss this, let R sub k denote the region, right, in the feature space where the Bayes classifier has got the value k for k equal to 0, 1. So we are assuming that there are two classes, class 0 and class 1, right? R0 is the region for which the Bayes classifier gives you the class label 0, and R1 is the region for which the Bayes classifier gives you class label 1, right? So as we have already discussed, right, when you're doing a classification problem, right, the Bayes classifier, it'll basically look at the joint density, right? The joint density of the observation, the feature that you have observed, right, and the class label, right? Which one has the higher joint density? Okay, based on that, it is going to spit out the class label. So it is going to give you the class label k, or x is in the region R sub k, if the joint density of x and y, right, that is the feature and the label, right, for the corresponding to the class k, and the vector that you saw, the feature vector that you saw, is greater than or equal to the corresponding joint density for the other classes. Okay, agree? So now this joint density f of x and k, okay, the joint density you can write as f of x conditioned on k times f of fk, right? And if you take the log, this is equivalent to x is in this region R sub k if dk of x is greater than or equal to dj of x, where dk is just the log of that function. Log of f, because the logarithm is a monotonically increasing function, okay? So you're not going to change the order by taking the logarithm, right? The ordering of those quantities. So you're going to look at this discriminant function, d sub k of x, all right, will be log of f evaluated at x conditioned on k plus the log of fk, right? Now, after this, to get your quadratic, no, that's again, I'm sure it's the code maroon, okay? Because they will send a text message also, yeah. So now, if the conditional densities are not, so you're going to make the assumption that the densities f of x conditioned on class 0, right, and f of x conditioned on class 1, these are normally distributed, right? So it's a multivariate normal, right? X is a feature vector, so it's a vector, it's not a scalar, so you're going to get a multivariate normal, and the typical density function for a multivariate normal random variable is given by this expression. You know that, where uk is the mean, kk is the covariance matrix, right? So now you're going to plug in these things into that discriminant, right? And now you have to compare, right? Is it going to be class 0 or class 1? Okay, which of these discriminants is larger, right? So you're going to compare. So now, so once you do that substitution, because you've taken logs and you already have an exponent in the density, so you're going to get like a quadratic form like this, all right? So the discriminant will become this function here, right? It's just, plugging the number, plugging the quantities into the discriminant expression. This form of this equation shows that the decision boundary dk of x, because the border is when dk of x equals dj of x, right? I mean, that's the border, right? So the decision boundary is clearly quadratic because you have x transpose some matrix x, right? So that's a quadratic function, right? So that's why this is called the QDA, or the quadratic discriminant analysis, right? So it has some assumptions, like you are assuming that it's normal, right? For each class, the density of the feature vector is normal, right? Now, so that's QDA. Now you want to go to LDA from there. That is linear discriminant analysis, where you'll have a straight line that will separate the two classes. So if you make the assumption that both the conditional densities possess the same covariance matrix K, right? Then in that case, you can drop this term, right? Because you're going to compare dk with dj, right? This thing, if both the classes have the same covariance, then as far as the capital K's are concerned, the subscript K is not going to matter, right? So this term will drop out, right? And your discriminant will look like this. It's just this term and then the next one, okay? Now here it says this is a linear function of x and produces hyperplane decision boundaries. It's not quite correct, okay? Because it's still not a linear function because there's a quadratic term here. However, when you compare dk with dj, right? Because both the classes have the same covariance matrix, all right? This x transpose kk inverse x, okay, is going to cancel out. So you'll be left with a linear function, right? And once you have a linear function, you know that it is going to produce a hyperplane decision boundary, a straight line, right? So now you can go a step further. If you assume that both the classes have got equal prior probabilities, that is fk, even this term also will drop out then. Okay, and you're going to get a linear discriminant analysis, right? A straight line. So you can go a step further. So when both classes have the same prior probabilities, then the discriminant characterizes what is called linear discriminant analysis, right? And this classifier will be of this form, where the class label that it spits out corresponding to a feature vector is basically a linear combination, right, of the components of that feature vector, right, plus some constant, and then you threshold this, right? So where x is x1, x2 up to xd, these are the components of the feature vector, and t will threshold at 0 and yield a -1 or a +1. So basically when this thing evaluates out to 0, right, that's the equation of a plane, right? When this evaluates out to 0, that is the boundary, decision boundary. And if it is greater than 0, then you will say that this thresholding function is giving you +1, right, for a particular class. When it is less than 0, it's giving you -1 for a particular class. So this is going to divide the space into two half spaces determined by the hyperplane defined by the parameters a0, a1 up to ad, right? And the hyperplane is determined by the equation formed from setting the linear combination inside the square brackets equal to 0. Right? That's the equation of a plane. Now, the equations for quadratic and linear discriminant analysis have been derived under the Gaussian assumption. Right? We assume that the density of the feature vector, right, given each class is Gaussian. Right? But in practice, they can perform well so long as the class conditional densities are approximately Gaussian. Right? They're used in places even when the Gaussian assumption doesn't hold. Right? And they seem to do reasonably okay. Now, if you're looking at the QDA, right, quadratic discriminant analysis, right, that has got more parameters because you have both the mean and you also have the covariance, right? So it'll have many more parameters. So if you have a small sample size, you're probably better off going with LDA, right, because it'll have fewer parameters. So, owing to the greater number of parameters to be estimated for QDA as opposed to LDA, one can proceed with smaller samples with LDA than with QDA. Right. Although the Gaussian assumption may not be satisfied, but with LDA you have to learn a lot fewer parameters. Now, although QDA, that is quadratic discriminant analysis, and linear discriminant analysis are derived under certain assumptions, they are often applied in situations where the assumptions are violated, right, in order to achieve parametric quadratic or linear classifiers. Right. I mean, engineers do that all the time. Okay, sometimes assumptions are violated, you still apply, and if it works, you're happy. Right? So in such circumstances, their performance depends on the actual feature label distribution, right, and the sample size. LDA appears to be more robust relative to the underlying assumptions than QDA. Right. So LDA does better. And again, these are just empirical observations. There's no theorem saying that that one is going to be better. All right, any questions? So we covered QDA, we covered LDA, right? And if you take a course on pattern recognition, I think Dr. Braganito will be teaching that next semester. I hope he's going to do some of these things. Okay, these are like basic, topics in pattern recognition. He might just do the math. Okay, I don't know, right? But you can look at the book by what's the name of that guy that wrote the book on pattern recognition? It's not Devore. Devore is the one that he might use. That's more mathematical. Who? Is that Bishop? I don't know whether they use that book. I thought the name of the guy was something else, the text that they use. It could be, So. Because all these topics are covered in that book in detail, right? So here we are just trying to go through it quickly because this is not a course on pattern recognition, right? We spent a lot of time learning molecular biology and transcription, translation, and so on. Now I'm just trying to show you that these methods will have applications over there, right, for carrying out gene-based classification of disease. Right? Now another classifier that is used, right, is called a support vector machine, right? So a popular classification rule to construct linear classifiers is what is called a support vector machine, right? And I think it's best explained using this picture, right? So here you have two classes, like these are the circles and these are the solid dots, okay? So these are coming from two different classes, and let's assume that the classes are linearly separable. That means you can separate the two using a straight line. So there are many different straight lines that you can use, right? But this thing here, this line in the middle, right, this is called the maximal margin hyperplane, okay? That is the one that is going to separate these classes, right, by the largest margin, right? And these guys, okay, this one here is called a support vector, and this is another support vector, okay, because that basically belongs to the data, right? And the maximal margin hyperplane has the property that it is going to be equidistant from the support vectors corresponding to these two classes. Okay, so it's in the middle, right? So that's a support vector machine. So let's just go through the text. So the figure shows a linearly separable data set and three hyperplanes. The outer lines pass through points in the sample data, and the third, which is called the maximal margin hyperplane, is equidistant between the outer lines. Okay, the outer lines are going through the support vector, right? So the line in the middle has the property that the distance from it to the nearest one label vector, well, here it was solid and circular dots, okay? So, but one of them you label as 1, the other one you label as 0. So it has got the property that the distance from it to the nearest one label vector is equal to the distance from it to the nearest -1 label vector. And the vectors closest to it are called the support vectors, right? And the distance from the maximal margin hyperplane to any support vector is called the margin, right? So half of that distance, that separation distance. And the matter is formalized by recognizing that differently labeled sets are separable by the hyperplane. The dot product of u and x equals c, right? That defines a hyperplane, right? I mean, because u is some vector, right? And x has got components x1, x2. So that's the equation of a plane, basically, right? So these are separable by this hyperplane where u is a unit vector and c is a constant. If the dot product of u with xk is greater than c, right? So if you take for one particular class, you take the dot product of u and the feature vector corresponding to that class, you're getting something greater than c, right? For the other class, you'll get something less than c, right? Then you can put that hyperplane u times x equal to c, right? And that's going to separate the two classes, right? So that's the main idea here. And for any unit vector u, the margin is defined in this fashion. That you look over all vectors belonging to the class 1, right? And you take the inner product between u and xk, the feature vector, right? And then take the minimum of these, because you want this guy, or you want c to be smaller than each of these guys, okay? As you go over all elements that have y equal to 1. See, if you look over there, see, you want c to be smaller than these guys, right? I mean, for all yk equal to 1. So if you choose c to be the minimum, okay, as you look over this entire class, right, then you'll satisfy, okay? And over there, similarly you want c to be greater than these guys, okay, for all vectors belonging to this class, where yk is -1, right? So in this case, you will choose basically c to be the maximum over this entire class. So that's what is being done over there, right? See, so minimum, right, for yk equal to 1, maximum over yk equal to -1, and then the distance between these two, half of that is basically the margin, right? And this maximum margin hyperplane, which is unique, it can be found by solving the following quadratic optimization problem. Among the set of all vectors v for which there exists a constant b, such that this is greater than or equal to 1 if yk is 1, less than or equal to -1 if yk is -1, find the vector of minimum norm v, right? And if you want to understand the details of this, just look at one of those books on pattern recognition. Okay, they'll have the detailed steps, right? Detailed explanation. And if v0 satisfies, if v0 is the solution, so you're trying to find the vector of minimum norm. So let's say v0 is that one you found by solving this optimization problem. Then the vector defining the maximal margin hyperplane and the margin are given by u0 will be the unit vector, right? You have to scale it down to v0 over norm of v0, and the margin is given by norm of v0 -1 respectively. And again, for these things, you can look at the book on any book on pattern recognition, right? I don't think that book is by Bishop. It's by somebody else. They use it as a text here, So maybe that's what you saw before coming here. So, but it has an orange cover. The book has an orange cover. Is one by Bishop with an orange cover? Probably not. Anyway, I mean, it's the book that is usually used for that class here, right? And it's pretty well written. Yeah. Now, if the sample is not linearly separable, like you cannot separate it with a hyperplane, right? Then you can do some approximation. You could get a good linear classifier. You'll make some mistakes, right? You cannot separate the sample completely. You can still stick in a linear classifier. You'll make some mistakes. Or the other option is you have to find a nonlinear classifier. Okay. And so in the first case, to get a linear classifier, you'll use the same kind of method that we've used, all right? Except that there will be some mistakes that will be made, all right? Now, second approach for a nonlinear classifier, what you could do is you could map it, all right? Maybe it's not linearly separable in this space, but you could find some mapping where in a higher dimensional space it looks like linear, right? They call it multidimensional scaling, right? So if you do that, then in the higher dimensional space you can find a hyperplane, right, or a line separating the two classes, and then you can map it back into the original space. And again, there are no theorems for this. You just do some trial and error, and do some mapping. Okay, any questions? Okay, now I give you an example where this is applied to. See, the only challenge here, so the theory of classification is no different than what is covered in standard books on pattern recognition. The only challenge here is that you have many, many features, okay, because you have thousands of genes on the microarray, okay. Which are the features that you're going to use to separate the different classes, okay, to carry out the classification? And the other thing is that the sample size is very small, so you do not have a whole lot of data to train your classifier, right? So there was this paper that appeared several years ago, right? And these papers usually appear in in journals like Science and Nature and all, okay? Because the classification is not new, okay? But if they apply that to gene expression from cancer samples, right? So in the case of breast cancer, there are, two different classes. There is a particular gene that will predispose people to cancer, okay? So these genes are called BRCA1, breast cancer 1, breast cancer 2, right? And so if people have a mutation in that gene, they're more likely to develop breast cancer, okay? So you want to see whether looking at the gene expression, right, across the entire genome, or at least across the genes on the microarray, right? Can you differentiate between the cases of breast cancer which are sporadic, right, versus the hereditary ones, right? The ones with the mutations in BRCA1 and BRCA2, right? So we illustrate some results based on regularized linear classification. In the case of breast tumors from patients carrying mutations in the predisposing genes BRCA1 or BRCA2, or from patients not expected to carry a hereditary predisposing mutation. So you have two classes of patients, right? Some people had mutations in that gene, right, BRCA1 or BRCA2, and others did not have any mutations, okay, but both developed breast cancer. So can you look at that, the gene expression, and can you differentiate between the two classes of people, right? That means the hereditary versus the ones with the mutations, right? So pathological and genetic differences appear to imply different but overlapping functions for BRCA1 and BRCA2. And in an early study involving expression-based classification, cDNA microarrays are used to show the feasibility of using differences in global gene expression profiles to separate BRCA1 and BRCA2 mutation-positive breast cancers, right? And that is shown in the. So here, see, they managed to find out two genes, okay, this one and this one, okay, and they are able to use a straight line to separate out the two classes. So one class is BRCA1 that has got mutation in that, and the other class is BRCA2 grouped together with the one that doesn't have the hereditary predisposing stuff, okay, and they were able to classify this, okay. Out of thousands of genes on the microarray, they were able to come up with this and this as the two variables that can be used to classify the cancers. Right. So using data from, let's see. So using data from that study, and I think this is a study that involved like 295 breast cancer patients or something like that, if I remember correctly. The analytic noise injection method has been applied to derive a linear classifier to discriminate BRCA1 tumors from BRCA2 and sporadic tumors. So these two are together one class. Okay, sporadic tumors, BRCA2 is one class. The other class they are interested in is BRCA1. The figure that I showed you shows the design classifier based on the genes KRT8 and DRPLA, along with its relation to the sample data pairs for these two genes. What can be inferred from this separation relative to population classification between the tumor classes depends on the method used to select the features KRT8 and DRPLA. See here, after these guys did the study, those two genes are given to us. We can see that they're doing a good job of splitting up the two classes. Okay, but to find those is not straightforward, right? Out of so many thousands of genes. So then the classification rule to construct the separating line and the relationship between the estimated error based on the sample data and the true classifier error relative to the feature label distribution. Because you have taken all these samples, you built the classifier, okay, you got the line that is separating these two. But the question is, now if you give it a new sample, right, is it going to put it in the correct class or not if you use this classifier, right? And to figure that out, you need to be able to do error estimation, right? Are you able to give an estimate of the error, how good your classifier is going to be on the general population, not just on the samples. Okay, any questions? Yes, sir.
I wonder if in the paper do they provide any user analysis?
Yeah. They will have to provide, otherwise it will not get published. So, but this paper is pretty old. It's like maybe 12, 13 years old. Right. So if you, I think it was in Nature. I'm not sure. Okay, either it's Nature or New England Journal of Medicine. Okay. So yeah. They will, but again, I mean, don't expect that they will come up with new intuition because these are pattern recognition methods, okay? So it's like some biology guys generated some biological data and they applied these methods. So don't expect that some biologist will apply that method and come up with some new method because this topic is what is referred to as feature selection, okay? That, which are the features, okay, that you're going to use to carry out the classification. And that is a classic, in pattern recognition, that is an old problem, right? That has been around for a long time, And we'll talk about some of the methods that can be possibly used, right? But I'm sure what they did must have been a trial and error of some, or a combination of these different methods, I mean, you cannot expect like a biologist to come up with a theory or to improve upon the theory of pattern recognition. It's very rare, but it's very unlikely that will happen, right? All right, any other questions? So now we come to the topic of feature selection, right? Now it turns out that, the Bayes error, it is monotone. That means if you increase the number of features, okay, you are going to decrease the Bayes error. So in theory, you're going to do better. The error of the best classifier is going to go down, okay, if you increase the number of features. But the problem is we have to live with classifiers that are designed based on the sample data, okay. For those, the error is not going to keep on decreasing if you just add more variables, okay. So the Bayes error is monotone, meaning that if A and B are feature sets for which the set A is contained in B, A is a subset of B, then the error that you get, the Bayes error that you get using the feature set B is going to be smaller than the Bayes error that you got using the feature set A. So thus, relative to the Bayes error, if one has a large set of potential features, it is statistically safe to use all of the features when forming a classifier, right? Which means on the gene, if you're doing a gene expression based microarray, you will use all the genes as potential features, but then you'll have 10,000 variables, right? And sample size is so small. However, if epsilon A sub n, A comma n and epsilon B comma n, these are the corresponding errors resulting from the design classifiers, not from the Bayes classifier, right? On a sample of size n, then you cannot assert that the expected value of, the one which contains higher number of features, right, is going to be lower than the expected value of the classifier using a smaller number of features, right? In fact, monotonicity does not apply to the expected errors of design classifiers. And it is in fact commonplace for the expected error of design classifiers to decrease. As you start increasing the number of features, initially the classifier is doing better, the expected error is going down, and then it'll go up, okay? So this is referred to as the peaking phenomenon, right? And that's captured in the next diagram, right? So this is the error, misclassification error, because we are concerned with the probability of making a mistake, right? That is the classification error. So initially when the number of variables is small, right, your error is pretty big. So this is the Bayes error, okay? See, the Bayes error is monotone. This is epsilon d. As you increase the number of features, right, the error goes down. But if you're looking at the actual error that you see when you're designing based on the sample, this error, as you're increasing the features, it initially goes down, and then somewhere it will turn around and go up, okay? So you should not be using too many feature variables, because then you are actually going to end up increasing the error. Yes?
Number of samples increase the expected error maybe approach to best error, right?
As the number of what?
It's number of
This is not number of samples, this is number of variables, the features.
sample of the expected value. Number of sample to compute the expected error. As number of samples is increasing small, and the expected error may be approached to the base error, right?
Yes. Yeah, but that'll be only, I think that rule has to be smart or something like that. Remember we talked about last time, yeah. Yeah, for smart rules, yeah. If the classifier is what, smart? No, see, but remember, all those things, when they're telling you that it'll go to the Bayes error, it'll approach the Bayes error asymptotically. It doesn't tell you whether it's for n equal to 100, 1,000, 10,000, million, okay? N equal to infinity means nothing, okay? Right, I mean, because, it could be 10 million, right? Yeah, you're right. When it goes to like 10 million or whatever, it may be that way, okay? But it's not necessarily true that, that effect you're going to see in this region, right? And usually what people observe is this peaking phenomenon, right? It goes down as you're increasing the features, right? But I don't know for what values of n they observe. Obviously you don't have resources to do up to n equal to infinity, okay?
Theoretically.
Yeah, theoretically when n goes to infinity, but see, infinity is an elusive quantity, so because for all practical purposes, you cannot wait for it. N is probably going to be 50, okay? In these applications, and if you're lucky if n is 100, right? So you're far away from infinity, right? So this peaking phenomenon does take place. So because of that, you just cannot keep on blindly adding more features, right? You have to be judicious, okay? So you have to do feature selection, right? And how do you do feature selection? So this peaking phenomenon is illustrated in the previous figure. I think that's what it's referring to. This is the peaking phenomenon. It's coming down, then it goes up as you increase the number of features, all right? So the peaking phenomenon is illustrated in the figure where the horizontal axis corresponds to a sequence of figures, correspond to a sequence of features, x1, x2 up to xd, and the vertical axis gives the error. So for d features, right, the Bayes error epsilon d continues to decline, but the expected error, which is the error of the design classifier, right, decreases and then it increases. One might hope that there is some way of avoiding checking all possible feature sets to find the best, right? Unfortunately, you cannot do that. Okay, there is a theorem, a classic result in pattern recognition, that in order to get the best feature set of size k, you have to check all combinations, all possible subsets of size k. Right? Somebody has already proven that, right? So a classical result states that to be assured of finding the optimal k element feature set from among n features, one must check all k element feature sets, unless one has some mitigating prior distributional knowledge, which is generally not the case in practical situations. Unless you have know something about the feature level distribution, you have no option but to try out each and every feature set of size k, right? Now, a further problem is that even were one able to check all feature sets, the need for error estimation can greatly impact finding the best one. Because, see, even if you're going to compare different feature sets, okay, you need to be able to estimate the error, right, with each of those feature sets. So that there is need for error estimation here. So it's not that straightforward, to come up with the optimal feature set, right? So you naturally, instead of going for the optimal feature selection, you will go with the suboptimal one, right? And there are different techniques that are available, right? Mostly ad hoc techniques, right? So the most obvious approach to suboptimal feature selection is to consider each feature by itself, right? One feature at a time, and choose the K features that perform individually the best, right? But that's not going to work because features, if you combine them together, they might do a lot better. Individually they might perform poorly, right? So while easy, this method is subject to choosing a feature set with a large number of redundant features, thereby obtaining a feature set that is much worse than the optimal. Moreover, features that perform poorly individually may do well in combination with other features, right? So a common approach to suboptimal feature selection is what is called sequential selection. So you don't do one at a time, right? Instead you do it sequentially, right? Either forward or backward and their variants. So sequential forward selection will begin with a small set of features, maybe one, okay? Then you will add one more feature to it, right? To see if you can do better. And you'll iteratively build the feature set. So when there are K features, all right, so you've already selected in the previous step x1, x2 up to xk, you've selected. So in the growing feature set, now you will consider all feature sets of this form, x1, x2 up to xk and then w, add one more feature, right? And then among these, you will try to pick the one which will give you the best error estimate, right? So that is going to be the feature set of size k plus 1. The problem with this is that once I added this w, right, when I add the next one, I won't take out w or for that matter anything that is building up in this list, okay? So whatever got into the list is going to stay in there, okay? So you don't want that because maybe once I've added a few more potential features, some of these are not needed anymore, right? Maybe they are dependent on those guys, okay? You should throw them out. So you do not want to do just sequential forward selection. You do forward and backward, okay? Add, then take off and all that. But again, it's trial and error, okay? And it's a combinatorial explosion, basically. So a problem with this sequential forward selection is that there is no way to delete a feature adjoined early in the iteration that may not perform as well in combination with other features, right? So the SFS look-back algorithm aims to mitigate this problem by allowing deletion. So for this sequential forward selection look-back algorithm, when there are K features up to xk in the growing feature set, all feature sets of this form, so instead of just adding one more feature, you add two more, okay? So K plus 2, you compare all of them, right? And then you choose the best one, okay? But now in one step, instead of going from K, you've gone from K to K plus 2, right? Now you'll take one of them out, right? So then all K plus 1 element subsets are checked to allow the possibility of one of the earlier chosen features to be deleted, the result being the K plus 1 features that will form the basis for the next stage of the algorithm, right? And you can add flexibility by considering sequential forward floating selection, where instead of adding one feature, you could add multiple features. You can take off also multiple features. So where the number of features to be adjoined and deleted is not fixed, but is allowed to float. Right. Again, these are all ad hoc techniques, right? There might be some theorems I don't know, okay, but people just use them in an ad hoc fashion. Now, when selecting features via an algorithm like this sequential forward floating selection that employs error estimation within it, because to compare the different feature sets, one should expect that the choice of the error estimator will impact the feature selection, the degree depending on the classification rule and the feature label distribution. In general, feature selection is an important and difficult problem with many proposed algorithms but little theoretical support, right? So to get back to your question about the breast cancer classification, how they carried out feature selection, all right, most probably it'll be some ad hoc technique that they pulled out from the pattern recognition literature, because I have got grave doubts that some biologists will come up with, feature selection algorithms, So for the most part, comparison of feature selection algorithms is via simulation, in which algorithms are applied to particular feature label distributions. And even if good feature sets exist, for small samples, the likelihood of finding one whose performance is close to optimal may be small. And this is due to the difficulty of classifier design and inadequate error estimation. When you have small samples, it's hard to design the classifier, right? Because a good classifier, and even the error estimation is also difficult because you have small samples, little bit of data. Are you going to use it for designing the classifier, or are you going to use it for estimating the error, okay? Or maybe you'll try to mix and match and all that stuff. So the problem is exacerbated for counting-based estimators like cross-validation on account of a multitude of ties among feature sets. There might be many feature sets that work equally well, okay? So then which one are you going to choose? So what's the tiebreaker going to be? So, all right, any questions so far? And again, I mean, some of you are going to work in genomic signal processing. I don't know if, is anybody over here working with Ulysses, Dr. Braganito? Yeah, you better pay attention to, or maybe you already are, error estimation, you know, because he's worked on error estimation a lot, okay? So error estimation is a key aspect of classification. If a classifier psi n is designed from a random sample Sn, right, random sample of size n, then the error of the classifier relative to the particular sample is given by epsilon n is the expectation over the feature label distribution f, right? That's one expectation. But again, the random sample, all right, is also a random variable. So you could take the expectation over those samples and you'll get the final error. So the expected error of the classifier, right, over all samples of size n is given by the expectation of epsilon n of this quantity. So you have to take two expectations, one with respect to the feature label distribution, and then you have to take the expectation with respect to the joint distribution of the sample Sn. Okay. And again, I mean, you guys are supposed to be the, what should I say, the experts in all this stochastic stuff. Okay, so I don't need to teach you that. Okay, you know that you have to take those two expectations, right? Now the problem is that in practice, the feature label distribution is unknown, right? And the expected error must be estimated, right? So you don't even know this distribution and you have to estimate this expected error. Now, if you have a lot of data, right, then you can split the data up into training data and test data. Training data you're going to use to design the classifier, right? To give it all these patterns. Okay, well, if the feature vector is this, you get this label, right? And so on, you train it many times, and hopefully then you can test it on some other data, right? So a classifier is designed on the training data, and its estimated error is the proportion of errors that it makes on the test data. Now the problem with using both training and test data is that one would like to use all the data for design, because increased data means decreased design costs. Just like you were pointing out earlier, right, that if you use more data, if n goes to infinity, right, you're going to approach the Bayes error, right? So you'd ideally like to do a better job of designing the classifier to decrease the design cost, right? But it's a problem with small samples. What are you going to do, right? You don't have tons of data, so are you going to use this data to do the design, right? Then how are you going to do the error estimation, right? Or how are you going to split up the data? So that's always a problem, and in the case of genomics, it's an even bigger problem because the sample size is typically small. If you're doing cancer classification, you'll be lucky if you get 100 samples, okay? The microarrays are not that, they're not dirt cheap, right? So, and it's quite labor intensive, right, running that stuff. So you're not going to get a lot of samples. Not to mention that the patients do not typically come and, you know, let you take tissues and biopsies all the time, right? So that you have better microarrays and you can satisfy the requirements of sample size and validate your error estimation. They don't care about that, okay? If they don't have cancer, they don't want to even hear from you, right? And if they do, then they just want to get well, okay, and move on with their lives, okay? They're not interested in in coming and donating tissue all the time. So different techniques are used, and again, I mean, these are all ad hoc, right? I'm just covering them just for your information because in papers, you know, in the genomics area, in bioinformatics and all, people use them all the time, okay? But I mean, theoretically, they are not on that kind of sound footing, you know. So one approach is to use all the sample data to design a classifier psi n and to estimate the error by applying psi n to the same data. So the training data is the same as the data that you use for testing, okay? Guess what? In that case, you expect that the results will be too rosy, right? Very optimistic, right? So the resubstitution estimate, as it is called, of the error is the fraction of errors made by the classifier that you design on the sample, which is also the training data. And resubstitution is usually going to be biased low, right? You're going to get a lower estimate for the error because the same sample that you use for designing the classifier, that's the one that you're testing on, okay? So the expected value of this error, epsilon n bar, the resubstitution error, will be less than the expected value of the actual error that you would get for the n samples, right? And it is often severely low biased when the samples are small. As with all error estimators, performance depends on the classification rule. An extreme example is that the resubstitution estimate is always 0 for the nearest neighbor classifier. Because see, if you give it the class label based on the nearest neighbor, right, that's the classifier. If you're going to do error estimation, right, then for that classifier you will get 0, right? Because again, the nearest neighbor is going to give you exactly the same label, right? Okay. Now, a common way of performing error estimation using the same data on which the classifier is designed is to apply a resampling strategy, and there are different strategies that people use. Cross-validation is a resampling strategy in which the classifier are designed from parts of the sample. Each is tested on the remaining data, and epsilon n is estimated by averaging the errors. So in k-fold cross-validation, what you do is you go ahead and break the data up. Let's say you have n samples, and you're going to break it up into k different parts with n over k in each one of them. Okay. Now you keep one of those samples, right? The n over k in each one of them. So keep one of them aside, and then you go and use all the rest of the data to design your classifier. Now you test it on the sample that you left out. Okay. And sometimes you leave out just one, and that's called leave one out estimation. So in k-fold cross-validation, right, the sample Sn is partitioned into k folds. That means in each of these folds you will have n over k points. Okay. Folds S sub I for I equal to 1, 2 up to k. Each fold is left out of the design process and used as a test set, and they estimate epsilon n CVK cross-validation, right? K-fold cross-validation, so CVK is the average error committed on all the folds, right? So you leave the first fold out, design the data on all the other folds, all right? Test it on this, look at the error. Then leave the second fold out, design the data on all other folds, again evaluate the error, and then average that out. That is the estimate that you're going to use. So a k-fold cross-validation estimator is unbiased as an estimator of expected value of n minus n over k, because remember you're leaving out n over k points, one fold. Okay, so it's the error that is estimated based on n minus n over k points, right? So meaning that the expected value of this error estimate, right, is the same as the expected value of n minus n over k, right? Now the special case of n-fold cross-validation, if k is n, then you have epsilon n minus 1. Okay, that's leave one out. Leave out 1 point, do the design on the rest of the sample, right, and then test it on that. Okay. So the special case of n-fold cross-validation yields what is called the leave one out estimator, which is denoted by epsilon hat n LOO for leave one out, which is an unbiased estimator of the expected value of epsilon n minus 1. Right. While not suffering from severe low bias like resubstitution, cross-validation, the problem is that it has got large variance in small sample settings, and therefore its use is problematic. Right. So if you focus on the unbiasedness of leave one out estimation, you can show that the expected value of this leave one out estimate, error estimate, will be expected value of epsilon n minus 1. So that, you know, the expected difference, right, between the leave one out estimate, right, and the epsilon n, right, the error that is made on the n sample, that is 0, right? So the expected difference is 0. But you're not, see, the problem is this expected difference is 0 means you're going to have positive errors, negative errors, okay? They're summing up to 0. But really, if you take the absolute value of the error on either side, right, you're having errors that cancel out, okay? But there will be wild swings, right? So for that, you need to look at the variance, right? So we're not interested in the expected difference between the error estimator and the error. Rather, we are interested in the precision of the error estimator in estimating the error, right? And our concern is this expected deviation, which is actually this with the absolute value inside. And that, in general, is not going to be 0. It can be far from 0, and especially if you have small samples, you know, the variance is going to be large, and you'll have a large value here. Okay, so this is also not a very good technique. Another resampling strategy is what is called bootstrap. And again, these are all ad hoc methods, okay? Somebody said leave one out, somebody will do k-fold cross-validation, right? The bootstrap is another method, right? It's a general resampling strategy which can be applied to error estimation. A bootstrap sample will consist of n equally likely draws with replacement from the original sample Sn, right? So you go and pick these out, okay, but with replacement from the original sample. So some points might appear multiple times in what you draw, whereas others may not appear at all. Now for the basic bootstrap estimator, which is denoted by epsilon hat ND, the classifier is designed on the bootstrap sample, right? That means the sample that you got out, okay? And tested on points that are left out, right? So you're drawing the sample, then you test it on the other points. And this is done repeatedly, and the bootstrap estimate is the average error made on the left out points, okay? Now epsilon hat ND tends to be a high bias estimator of the expected value of epsilon n, since the number of points available for design is on average only 0.632n. Okay. And I don't know how exactly that computation is done. I have not looked at the paper. I'm not a pattern recognition person, but I'm sure that somebody has done that calculation. Right? Maybe the pattern recognition book has that. So this is high biased, okay? But at the same time, the resubstitution error is low biased, okay? So somebody came up with this brilliant formula, okay? They call it 0.632 bootstrap, where you're going to weight one of them by 0.632, the other one by 1 minus 0.632, that is 0.368, right? And that is the 0.632 bootstrap estimator, right? Again, I mean, does it have special properties? Probably not, but they justified the choice of 0.632 and, and the biologists have gone and used all of these, okay? Because, I mean, there are a lot of papers where they have used different estimators, different classification rules and so on, okay? About 10, 12 years ago, that was the time when, you did a microarray experiment and then you use the gene expression, do the classifier. I don't think you really contribute that much to the theory of classification, all right? But you have new data and it's interesting, and papers of that type have appeared in top of the line journals like Science, Nature and all that, with impact factors of 30, right? But you have to be the first one. If you try to do it right now, probably they'll just throw it out, okay? Because too many people have already seen it. Now, next I move on to a discussion of bolstered resubstitution estimator, right? And if you take the course with
gas leak repair. Student rec center reopened. Resume normal activity. 1:26 p.m.
That's okay. Someday if you have somebody with a gun and all that, we're not going to be laughing, right? So now in resubstitution, so if you take a course with Dr. Braganito, right, because he's worked on this bolstered resubstitution estimator, right? So he will talk about this more, okay, in 649. So in resubstitution, there is no distinction between points near and far from the decision boundary. The bolstered resubstitution estimator is based on the heuristic that relative to making an error, more confidence should be attributed to points far from the decision boundary than points near it. Like if you look at this picture, right? So if you make a mistake, all right, far away from the decision boundary, if there's a point here, okay, that really should have been on the other side, it's a mistake that you still can live with. But if something is way inside, okay, and there's a mistake over there, that's a much, much graver mistake, right? So because of that, right? Yeah, they're trying to keep us safe, so that's okay. So because of that, you'll do, so the shaded area, okay, this one shouldn't have been here on this side. So you're putting a bolstering kernel around it and you're going to give it a bigger weight, okay? Similarly, this one will have a lot of weight because it's a plus that is appearing on the wrong side, right? And here also, if it's close to the boundary, you put a kernel around it because it's too close to the boundary, right? Right, so I put some weight on it because there is a portion that would still go jar onto the other side, okay? So you basically put some weighting function, some kernel, right? And then you integrate that to get the error estimate. So the bolstered resubstitution estimator is based on the heuristic that relative to making an error, more confidence should be attributed to points far away from the decision boundary than points near it. And this is achieved by placing a distribution which is called a bolstering kernel at each point and estimating the error by integrating the bolstering kernel for each point over the decision region that the point should not belong to and then summing the integrals rather than simply counting the number of misclassified points as in resubstitution. And the procedure is illustrated in the figure for a linear classifier. And a key issue is the amount of bolstering, that is the spread of those kernels, okay, how much they should be spread out. And to get a better idea about that, you probably have to take a look at at Dr. Braganito's paper. Right. All right, any questions? I think we are almost done, but probably I will just stop here because I think we are running out of time, and then on top of that, there's this thing that keeps coming up. So next time I will finish off the classification chapter and I will go on to clustering.